Today's topic of discussion is the points where derivative does not exist. So if a function is differentiable, then it is continuous. A differentiable function is continuous, but converse is not true. A continuous function may be differentiable or may not be differentiable at certain points. So differentiable function is always continuous, but continuous function may or may not be differentiable. If a function is not continuous, then derivative does not exist at those points where function is not continuous. So wherever your function is non-continuous, derivative does not exist at those points. If derivative from left and derivative from right are different, or limit from left and limit from right are different, then derivative does not exist at that point, because derivative is the slope of the tangent line. If you cannot draw a tangent line at the particular point, if you're drawing two tangent lines, then we're not sure which one to use. Which tangent line slope is going to be the derivative. Derivative does not exist at corners, sharp points, and vertical tangents. So here's some examples. Find each limit. Limit x approaches -1 f of x. So x approaches -1 f of x. Does the limit exist? No, the limit does not exist, because coming from the left-hand side and the right-hand side, limits are different. If the limit does not exist, there is a discontinuity here. The derivative will not exist at point -1 either. Limit x approaches 0 f of x. So when x is approaching 0, what is happening to the limit? Again, it does not exist. Coming from left-hand side and right-hand side, I'm going to two different y values. So limit does not exist, and the derivative does not exist either. Now let's check out limit x approaches 1 f of x. So when x is approaching 1 f of x, does the limit exist? Yes, the limit does exist. Limit is 1. Limit x approaches 2 f of x. When x is approaching 2, the limit is going to be, the y values are approximately 3.5. Now we just said the derivative does not exist at corners, sharp points. Why is that? Because we don't know what kind of tangent line to draw at the corner. So at this sharp point, should I draw a tangent line like this, like this, like this? Which tangent line is okay for this point? Same thing here. Which tangent line would be acceptable, or which tangent line should I go with? So there's many possible tangent lines, or no possible tangent line here, and thus there is no slope of that tangent line. Let's see, state the number at which f is not differentiable and give reasons. So here, at which points is the function not differentiable? Looks like the function is not differentiable at -4, and function is not differentiable at 0. Because at -4, there's a sharp corner, and at 0, there's a discontinuity. The function is not continuous. The next one looks like at x equals 4, the function is not going to be differentiable because of the sharp corner. Again, the same thing, we don't know which tangent line to use for the sharp corners. Differentiability implies continuity. That means if a function is differentiable at x equals c, then f is always continuous at x equals c. On the other hand, if f is continuous at x equals c, it may or may not be differentiable. Here we're going to look at an example. F of x equals absolute value of x. It is continuous, so we're going to show that it's continuous, but it's not differentiable at x equals 0. Let's look at graphically. We know the graph of absolute value of x. It looks something like this. We can see that this is continuous. We can draw the graph without picking our pencil. It's continuous, but why is it not differentiable at x equals 0? Because there is not just one possible tangent. And we talked about the limit definition of derivative. In order for the limit definition to work, both one-sided limits should exist, and they have to be equal. Coming to c from the left-hand side and coming to c from the right-hand side, both of these limits should exist, and they have to be equal. If they're not, then the derivative will not exist at that point. So let's check at this point x equals 0. So I'm going to do limit x approaches 0 coming from the right-hand side, absolute value of x, and limit x approaches 0 from the left-hand side, absolute value of x. So we're going to use the limit x approaches, so we can say absolute value of x. We know the definition of absolute value of x. Absolute value of x is equal to, absolute value of x is equal to positive x if x is greater than or equal to 0. It's opposite if x is less than 0. So we can use the Let's go ahead and find both left and right-handed sided limits here. So limit h approaches 0 from right-hand side, 0 plus h minus absolute value of 0 divided by h, because it would be your point x is 0. So x plus h minus f of x divided by h, x minus h. So that is going to leave us with h over h, and that's equal to 1 because absolute value of h is equal to h. And if I'm coming limit h approaches 0 from the left hand side, 0 plus h minus 0 divided by h. Now this piece is going to equal negative h. Absolute value of h when I'm coming to 0 from the left hand side is going to be negative h minus 0 divided by h, which would be negative 1. So both the limits are different. The limit h approaches 0, h approaches 0 of f of x minus f of 0 over x minus 0 does not exist. So this limit does not exist. Actually, I should write it in the h terms, not in the x terms. So this limit does not exist. Limit h approaches 0, f of x plus h minus f of x over h. So this limit does not exist. If this limit does not exist, then we would say absolute value of x is not differentiable at x equals 0. So it's not differentiable at x equals 0. Right, let's see a couple more examples. We just said that for the limit definition of derivative to work or the derivative to exist, both one-sided limits have to be equal to each other. Both one-sided limits should exist and they have to be equal to each other. So let's look at a graph with a sharp turn. Consider the graph of absolute value of x minus 2. Again, at point 2, we don't know what kind of tangent we should draw. So we're going to evaluate both one-sided limits. Limit x approaches 2 from the left hand side, limit x approaches 2 from the right hand side. So limit x approaches 2 from the left hand side, because I'm coming to 2 from the left hand side, the definition says this is equal to x minus 2 if x minus 2 is greater than 0. Let me give myself more space. So absolute value of x minus 2 is equal to x minus 2 if x minus 2 is greater than 0, which means x is greater than equal to 2. It's equal to opposite of x minus 2 if x is less than 2. Actually, both of these cannot have equal sign. Only one can have equal sign. So I'm going to give equal sign to the top function, x minus 2 greater than equal to 0. All right, so coming to 2 from the left-hand side, this is going to equal f of x would be negative x minus 2, and f of 2 would be 0 divided by x minus 2, which is negative 1. And coming to 2 from the right hand side, the absolute value of f of x would be x minus 2, no negative in the front, and f of 2 is 0 divided by x minus 2, which is going to equal positive 1. So both one-sided limits are different, thus the derivative does not exist. F of x is not differentiable, and has no tangent line at x equals 2. F of x is not differentiable and has no tangent line at x equals 2. Even though it's continuous at that point, but the derivative does not exist. Let's look at a graph with the vertical tangent. A graph with the vertical tangent, f of x equals x to the power 1/3. This function is continuous at x equals 0 because there's no holes, no gaps, no jumps. But because the limit, let's go ahead and evaluate the limit as we are approaching 0. So x to the power 1/3 minus 0 over x minus 0. That leaves me with limit x to the power 0, limit x approaches 0, limit x approaches 0, x to the power 1/3 over x, and we are going to subtract the exponents. 1/3 minus 1, 1/3 minus 1 would be limit x approaches 0, x to the power 1/3 minus 1 is negative 2/3, which is going to be limit x approaches 0, 1 over x to the power 2/3. And this limit does not exist because it gives me something undefined. 1 over 0 is undefined. So derivative does not exist at point 0. So remember, the derivative does not exist at sharp corners, vertical tangents, anywhere your function is not continuous, or both one-sided limits are not equal to each other. Let's look at a few more functions and see if they're differentiable or not. We're going to look at them graphically. You can also use the limit definition. So let's go ahead and look at the graph of x to the power 2/3. That's how the graph of x to the power 2/3 look like. Is that differentiable at 0? No. So not differentiable. Not differentiable at x equals 0. Next we have the cube root of x. Cube root of x looks something like this. And again, looks like there's a vertical tangent. This is going to be not differentiable at x equals 0. Absolute value 2 minus absolute value of x, that is going to be an absolute value of x graph shifted, flipped and shifted 2 units up. Not differentiable at x equals 0. Not differentiable at x equals 0. That's all for this video. So remember, the function, if a function is not continuous somewhere, then the derivative does not exist. Derivative does not exist if both one-sided limits are, if the limit from left hand side is different from the one from the right hand side. If the limit is different, limit coming from the left hand side is different to the limit coming from the right hand side, then the derivative does not exist. And derivative does not exist at sharp corners, at sharp points, and vertical tangents.